Hi, so today we're going to start talking about two-dimensional motion. This chapter will take us about 2 weeks to cover. Depending on your mathematical ability and how well you were doing with the kinematics, this chapter can be a little bit easier or harder. If you need a little bit of review on the kinematics, you want to make sure that as you go through this, you pay special attention to the mathematics. Many students will do well in this chapter, but you're going to need to make sure that you can solve the problems that we are going to cover. It's very specific. There's very specific problems that you need to be able to understand how to solve. So please pay close attention to that as we go through this. Here we go. So back at the beginning of chapter 2, we started talking about the fact that where an object is, its position is very important in our understanding of the universe. If we do not know the position of an object, we cannot describe anything else about the universe. And so identifying where something is, its position, is very important. If I have an object and it is located here, and then it has, and I know it's right there, and then I come back later on and it's now here, you can identify that there has now been a change in position. If I didn't know where it was initially, then I would not be able to identify that that position changed in the second return. And so when we recognize that an object changes position, we recognize that displacement happens. Displacement is the change in position. That leads to a whole pile of questions. How fast did it change? How long did it change? How fast did it get faster? These are the kinematic questions. Final velocity, initial velocity, acceleration, displacement, time. The 5 key things we look at with the kinematics. So average velocity is how fast an object has displaced itself. It's the displacement divided by the time. The average acceleration is going to be referring to how fast the velocity itself changed, how fast we got faster. So that's a little review, and we are going to use these terms as we continue to move on. There are really 2 ways that an object accelerates. We say that whenever velocity changes, whenever there's a change in velocity, then acceleration occurs. So delta V means that A has happened. And so the idea of velocity is that it has 2 different values connected with it. It has a magnitude and a direction, because velocity is a vector. So there could be magnitude or there could be directional change. We have only to this point talked about magnitudal change. A car is driving down the road and somebody hits the gas pedal and it goes faster. Or the car is driving down the road and somebody hits the brakes and now it slows down and it stops. We've sped it up, we've slowed it down, we've changed the magnitude of the velocity. But a car going down a road and going around a corner at a constant speed, look at the speedometer, you can travel down the road at 55 miles an hour and go around a corner at 55 miles an hour. The speedometer doesn't change. That has a change in direction. And so when we're talking about the idea of acceleration changing velocity, it's not just changing velocity in terms of its magnitude, but it's also changing its velocity in terms of its direction as well. It's really important that we understand that velocity changes 2 ways, either by magnitude or direction. We can change both, but you need to recognize that so far we've only talked about magnitude, but we're going to talk about direction a little bit now. So specifically, we're going to talk about projectile motion. Projectile motion is the idea that an object, when fired, thrown, kicked, flies through the air, and the only thing influencing it is gravity. Gravity is pulling down on it. This is a force. We haven't talked about forces, but we talked about the impact of that force, that the acceleration in the y direction is equal to g. The acceleration in the x direction is going to be equal to 0. There had to be some initial velocity to get our object moving, but once it's in the air, it will continue to move. Imagine a desk. I have a desk and a ball on the desk, and I push the ball off the desk at some velocity. If the desk were to continue on, the object would just continue to roll. But if there is no shelf there to have it continue on, when the ball rolls off, it starts to fall downward. Gravity starts pulling down, and as the ball is going forward, it will continue to move forward. So if I have two objects rolling at the same speed, one rolling straight across, one rolling off the edge of a cliff, they will stay in line with each other because the acceleration in the x direction is zero. Again, we had another freeze here. I have a ball launcher. There's an object up here, and one ball is attached on this side. Another ball is attached, say, on a tray or something on this side, and the ball is shot sideways. So this ball starts to drop. This ball on the right starts to drop, and this ball here is shot sideways, and that all happens simultaneously. They start off at the same height. Which hits the ground first? The answer is they both hit the ground at the same time. That's because the minute this ball leaves, gravity starts pulling down. The minute this ball is released, gravity starts pulling down. If they're at the same height, the acceleration due to gravity is going to make them fall to the ground in the same amount of time. The faster I shoot the ball horizontally, the further it goes. We'd have different lengths of the range, how far out it goes. Those will be dependent on how fast it's moving in the x direction, but gravity is going to pull it down, and so each of these balls will reach the ground at the same exact time if they were released at the same exact height. And again, that is because gravity is like a bad friend. It's always dragging you down, 9.8 meters per second squared. An object moving in both the x and y direction simultaneously is moving in what we refer to as two-dimensional motion. So this here on the right, this is one-dimensional. On the left, this is two-dimensional. It's moving xward and yward at the same time. If the only force acting on it, the only thing accelerating it after it's started moving is gravity, then we say that is projectile motion. If there's a rocket booster, if there's an engine, if something else is applying a push to it, then we would say it's two-dimensional, but it's not necessarily projectile motion. Okay, so this graph here is an important one to take a look at. We're going to look at this using the FED app. Here we go. FED app. When we shoot a projectile through the air, the object flies up into the air, and you will see here that there are some vectors. I'm going to zoom in on this a little bit with the hope that you can see us a little bit more, and I'm also going to move our cannon down a tiny bit. Let's see what happens now. There we go. I'm going to turn off some air resistance. I'm going to lower the speed. Beautiful. I hit the target. Great. So what we see here, and if we do this in slow motion, what we see here is going to be a projectile flying through the air. The green lines that you see there represent the velocity. And so as the object is flying through the air, what we will identify is that the object itself will move up. The velocity will, the vertical velocity will decrease, and the horizontal velocity will remain the same. Watch the line that's pointed to the right. It does not change in length. It does not change in length through this entire flight. Now watch the line that's pointed vertical. It's decreasing. It reaches zero. It starts going negative. If I were to stop this, let's say right here. Whoops, I missed that. Let's try this again. If I were to stop this right here, I'm going to make a mark on my screen. I'm going to bring a line straight across. I'm going to try to stop it right there on the other side. Take note of this length. Now we let this fly to the other side. Ignore the one at the top. How does this length here compare to this length here? Well, they're opposite in direction, but I think if you were to measure them at the exact same height, you would find that their lengths are exactly the same. They're opposite in direction. We talked about this when we talked about throwing a ball up in the air and then having it come back down. When it reaches the top of its path, its velocity is equal to zero. At any given point, the velocity up and the velocity down are equal in magnitude, opposite in direction. And so as we're watching these projectiles fly through the air, what we should see is that they have exactly the same magnitude at exactly the same height, different directions. That's important that we identify that. Now, the reason this happens is because the velocity in the x direction is not changing. It's constant because there is nothing pushing or pulling it. The acceleration in the x direction is 0. The velocity in the y direction is moving towards the negative. And the reason that's happening is because the acceleration in the y direction is equal to negative 9.8 meters per second squared, equal to gravity. And so as this is flying through the air, up through the air, when it reaches here, there is a horizontal velocity. And that horizontal velocity is the same as the horizontal velocity here, and the same as the horizontal velocity here, and the same as the horizontal velocity here, because the acceleration in the x is 0. The acceleration in the y is becoming less, it becomes 0 at the top. I actually take that back. It starts off, it says it's becoming less, but it starts off in the positive direction, becoming less. It's 0, then it starts to go back down, becoming greater down, becoming really great down. And so that is how a projectile travels through the air. That's the impact of the acceleration on that projectile. Watch it again. And you could see that happening. Now, back to our notes. Our notes are going to show us exactly what we just described, that the acceleration in the x is 0. We also see that we can break our values down into, if I shoot an object, a ball, 40 meters a second at 20 degrees, well, I can break that down into its y component and its x component. X is going to equal the initial velocity times the cosine of theta, and the y value is going to equal the initial velocity of y is equal to v sine theta. So we're able to find the components, which are going to be important when we solve equations like this. It is also important to recognize, again, the g value is always going to be 9.8. Together, these are going to create the basis to do kinematic problems in 2 dimensions. I'm going to make another video for you where I go through a sample problem for you to see, and then we'll do some more problems next week. If you have any questions, let me know.